All right, let's talk about the elliptic curve method of factoring whole numbers. So I'm going to start with the Pollard P-1 method. This is a different method of factoring integers that the elliptic curve method is based on. Then we're going to be working with elliptic curves over finite fields. I want to talk briefly about that. And in particular, there's a nice estimate for the number of points on these elliptic curves. So you get these finite groups where the order of the group is roughly equal to p in size. Then we'll talk about how do we calculate the sum of the points on these elliptic curves. So we're starting with some integer m that we wish to factor, so we're going to be working mod that given number m, and then go through Lenstra's elliptic curve method of factoring, the ECM method, and talk briefly about the effectiveness of this method. Okay, first the Pollard P-1 method. So suppose I have a large number m that I want to factor. Then for any natural number k, I'll let Lk denote the least common multiple of the integers from 2 up to k. So what does that equal? Well, there'll be some power of 2, so say 2 to the e1, and that power of 2 will occur somewhere in this list. And that'll be the largest power of 2 occurring between 2 and k. And then there'll be a 3 to some power e2, and again that power will occur somewhere in that list, and so on. So you'll get a product of these prime powers where these are maximal prime powers sitting below k. Alright, let's suppose that m happens to have some prime factor p such that p-1 is a divisor of Lk. That is, all of the prime power factors of p-1 are less than or equal to k. What can we do in this case? Well, by Fermat's little theorem, we know that 2 to the p-1 is congruent to 1 mod p. And since Lk is a multiple of p-1, that would say that 2 to the Lk is congruent to 1 mod p. In other words, p is a divisor of 2 to the Lk minus 1. Now, what we'll do is we'll just go ahead and calculate the GCD of m and 2 to the Lk minus 1. Let's call that value d. So then this prime p, it was given to be a factor of m, and it's also a factor of 2 to the Lk minus 1, and so p would be a divisor of this GCDD. And so that greatest common divisor is strictly bigger than 1. So if in addition that divisor d happens to be strictly less than m, then d is a proper divisor of m bigger than 1, and so we've made progress in the factorization of m. Now this value m, the GCD of m and 2 to the Lk minus 1, can be calculated very rapidly. So what we do to calculate that value is use modular exponentiation. I first just find the value of 2 to the Lk mod m, so let r be the least residue we end up with. And then using the GCD invariance property, I can just subtract that appropriate multiple of m from 2 to the Lk and reduce this term to just r minus 1. And so now we have a very small number right here. This is some value less than m, and we can just use the ordinary Euclidean algorithm to calculate d very rapidly. Now in practice, the question is, how big should we take k to be? So k was this parameter. So we typically let it be like 100, calculate the GCD, and then let it be 200, calculate it, let it be 300, and you keep going until you just get tired of running this particular algorithm, and you hope that at some point in the calculation of this GCD you're going to get a value strictly between 1 and m. So when are we going to be successful with this algorithm? So we will succeed in factoring m, provided m happens to have some odd prime divisor p, such that all of the prime power divisors of p minus 1 are less than or equal to k. And we need that extra little stipulation here. But this is the key fact here. We want all of the prime power factors of p minus 1 to be less than or equal to k. And you may wonder, well, is that very likely? And it turns out that, yeah, occasionally you are going to get successful. There's a good percentage of large numbers that have all small prime power divisors. In fact, I'll give you a homework problem where you can actually estimate how many numbers have that condition. So if we want to calculate, here's the homework problem. What's the probability that a number chosen at random from 1 to x has all prime power divisors less than or equal to 100, let's say, and it's given roughly by this expression right here. So let's say x is a 20-digit number, then roughly 10% of the 20-digit numbers have all of the prime power divisors less than or equal to 100. And so you would be successful in implementing this method if p minus 1 happens to be one of those 10%. And you can see that the likelihood of success goes way down as the number of digits of the number goes up here. So in the Pollard P-1 method, we're working in the group of units mod p. This is where we used Fermat's little theorem. And the method was successful if the order of that group, so the order of the group is p-1, has all small prime power divisors. Now our goal is to come up with other types of groups we can do the same type of game with. So rather than just focus on groups of order p-1, it would be nice to work with groups whose order is p-2 or p plus 1 or p plus 3 or p-7. And so you'd have lots of different group orders where you can hope that one of those orders is going to have all small prime power divisors. And that's where the elliptic curve groups come in. So in order to get these groups whose orders are p plus or minus some small number k, we use elliptic curves over finite fields. So let's turn now to Lenstra's ECM method, the elliptic curve method for factoring numbers. So we're going to be working over an elliptic curve defined over a finite field fp. So let's let, again, m be our big number that we wish to factor. And let's assume that m has no small prime divisors, say up to about 10 to the 5th power. I mean, those primes you can check very directly. So we're only going to be searching for prime factors bigger than 10 to the 5th. And then I'll let a be a parameter 1, 2, 3, up to 10,000, let's say. And let's let C sub a, denote the elliptic curve over the finite field fp, defined by this equation right here. So this is our canonical equation, y squared equals x cubed minus ax plus a. And the reason I've picked this very simple form here is so that I can identify immediately a given point on this curve. So 1, 1 is trivially a point on this curve. The discriminant is given by a squared times 4a minus 27. And so as long as the prime p is not a divisor of a or a divisor of 4a minus 27, we get a non-zero discriminant, and so we have a genuine elliptic curve. And since my assumption was that p is bigger than 10 to the fifth, you can see that the discriminant of all of these curves is going to be non-zero, and so we do get a true elliptic curve. Okay, I'll let GPA denote the additive group of points on this elliptic curve. So that's all points whose coordinates are in the finite field FP. I'll let capital N denote the cardinality of that group. And there's a famous formula of Hasse that says this number of points is very close to P. So it says that N minus the quantity P minus 1 in absolute value is always less than or equal to 2 times the square root of P, meaning that the number of points on your elliptic curve is P plus or minus some small number K, where the absolute value of K is bounded by 2 times the square root of P. And so we get all of these different group orders. As we change the parameter A, we get a group with a new value of little k right here. And so we get all sorts of different groups that we can be working in. So this time we're going to be successful obtaining some non-trivial factor of our given number m, provided that one of these group orders, p plus or minus k, happens to have all small prime power divisors for some prime factor p of m. So we've increased our likelihood of success by not just considering one group, but considering lots of different groups. So we let A roll through a variety of elliptic curves, and we have a lot more chances for success here. But wait a minute, you say. In order to implement this algorithm, we need to be working over the finite field Fp, where P is a prime divisor of M. Well, if we knew that prime divisor ahead of time, we would be off to the races and we would be factoring M from the start. So the question is, we are given this big number M I'm trying to factor, and I don't know this prime P. So how do I work with this elliptic curve, which is an elliptic curve over the finite field Fp? Okay, so keep that in mind. We'll see how we do that. So let's recall our addition law for elliptic curves. And this is exactly what we did last time for the rational numbers. So if I want to add 2 points P and Q on the elliptic curve, the formula looks like this. So x3 would be the slope, m squared minus x1 minus x2. y3 is mx1 minus x3 minus y1. And if I want to just double a point, add p to itself, then we had this formula right here. So x3 and y3. So here's how we get away not knowing what p is. When I'm doing the calculations of these values, x3 and y3, instead of working mod p, which is really what we want to be working in for the finite field, we do all of the arithmetic mod m. Now m is our given number, so I can do arithmetic mod m. And now you just use the fact that if two numbers are congruent mod m, then they will also be congruent mod p for any prime divisor p of m. And so these formulas are going to be valid for any prime factor of m. And that's how we get away not knowing what p is. Now it turns out there's a better way of doing these calculations so that we don't need to be dividing. Well, division in mod p would mean multiplicative inverses. And that's based on the following theorem. So we can characterize rational points on an elliptic curve as follows. So I'll let CFQ be an elliptic curve defined over the rational numbers. Then I claim any point with rational coordinates on that curve must look like this. So these are reduced fractions, but notice there's a relationship between the denominators. The denominator of the x coordinate is a perfect square of a whole number, and the denominator of the y coordinate happens to be w cubed. So u, v, and w are integers, with u and w relatively prime and v and w relatively prime. Okay, so I'll go through the proof of that on the next slide, but let's just point out how we do the arithmetic then. So if P and Q are the given points on the elliptic curve, so that's a V1 over W1 cubed right there, and you want to perform the addition using the formulas we saw on the previous page, well, you're going to end up with a point that'll have some denominator of the form W3 squared and the denominator here of the form W3 cubed. And when you do the algebra, you'll come up with these formulas for U3, V3, and W3. So U3 looks like this algebraic expression, V3 is like this, and there's a similar algebraic formula for W3. And these are just polynomial expressions, so you never need to compute inverses mod m. And this makes the algorithm much more efficient to work with. And there's similar formulas for doubling a point. So 2 times p would look like this, where u3, v3, and w3 are given by these formulas. So by using these formulas, we can compute successive multiples of a given point on an elliptic curve without ever needing to calculate a multiplicative inverse mod m. Now, if you wanted to find the explicit points at each intermediate step, so these points right here where you'd have this w3 in the denominator, you have to interpret this as a multiplicative inverse mod m. But we will actually never need to do this. Okay, let's go back and look at that theorem. So why is every rational point having this special form like that? So let's let xy be the given rational point on this curve. I'll write x as a reduced fraction, u over z, where u and z are relatively prime. And then I'll write y as some reduced fraction, let's say alpha over beta. And then I want to turn that fraction into this form, so I'll just multiply top and bottom by this denominator z, like that, and then just write it as alpha z over beta times 1 over z, and then reduce this fraction right here. So when I reduce this fraction, I'll call that v over d times 1 over z, where this is now a reduced fraction. And so that's how I'm getting these forms right here. So x is of this form, and y is of this form, where u and z are relatively prime, v and d are relatively prime, and I can assume that the denominators are all positive. Okay, then insert this into the equation of the elliptic curve. So y squared on the left equals x cubed plus ax squared plus bx plus c. Multiply through by z cubed and multiply through by d squared on the whole equation, and I get v squared z equals d squared times the quantity u cubed plus a u squared z plus b u z squared plus cz cubed. Thus, z is a divisor of d squared u cubed. Okay, where does that come from? So z is in every term and therefore it must be a divisor of the first term. But z is relatively prime to u, so by Euclid's lemma, z is a divisor of d squared. Also, I claim that d squared is a divisor of v squared z. So d squared times some integer equals this. Well, okay, that's trivial. And d is relatively prime to v, so d squared must be a divisor of z. So we've got z divides d squared divides z. These are positive numbers, so z must equal d squared. And that says x is u over z, so u over d squared. Y is v over d cubed. QED. Okay, here's our procedure then for factoring a given number m. So I'm going to start with the point P0 equaling 1, 1, which is clearly a point on this curve. That's why we chose the curve to have this simple form. Again, we'll set Lk to be the least common multiple of the whole numbers from 1 to k. And I'll let k go 100, 200, and so on. And we want to calculate Lk times P0. So we're in an additive group, so we just keep adding P0 to itself, and we calculate this by doing successive addition. And by calculating this, I mean let's calculate the successive u, v, and w values that we wrote the formulas down for. And you keep going until Lk P0 is the zero element of the group, P infinity. Or maybe you've exhausted your allotted computer time, or you say, okay, we've gone on long enough and I haven't hit the zero element, and so let's try a new elliptic curve and see if we can be successful. So now this is completely analogous to what we did in the Pollard P-1 method, where we started with a given number 2, so that's kind of corresponding to our given point P0. This was a multiplicative group, so we raised 2 to the Lk power, and we wanted to hit the identity element. So how do we identify when we've hit the zero element of our group? So recall the zero element on your elliptic curve in the projective plane is the point 0, 1, 0. So we are calculating values of this type here, a u over w squared comma v over w cubed. And in the projective plane, put the colons in here, that would correspond to this point, and then I just cross multiply through by w cubed, and so we get uw v w cubed. So when am I at the point 0, 1, 0? We're at that point precisely when w equals 0 in the finite field fp. And so that's why I say we never actually have to compute these fractions, the u over w's. We just calculate the u, the v, and the w, and we keep going until we get a value of w that's 0 mod p. So let's suppose that the number m, the number we're trying to factor, has a prime divisor p such that this group order is comprised of prime powers less than or equal to k. Well, that would mean that the order of this element 1, 1 is a divisor of Lk. So Lk times 1, 1 is the zero element. That is, w is congruent to 0 mod p, which means that p is a divisor of both m and w. So now, in implementing the algorithm, we simply calculate the GCD of m and w. And by calculating this GCD, we'll obtain a divisor of m bigger than 1, and hopefully less than m, And so that will make progress in factoring the number m. So it's completely analogous to what we did in the Pollard P-1 method at this point. So in summary, we start at our given point, 1, 1. We compute this multiple, Lk times P0, for a suitable value of k using the formulas we have above, but working mod m, which is a given number. We let W3 be the resulting value coming from that calculation. We calculate the GCD of W3 and m, and if this value is strictly between 1 and m, we are done. We have succeeded in getting a proper factor of m strictly between 1 and m. Otherwise, we can opt to change the value of k, or we can change the value of a and come up with a new elliptic curve and try again. So if m happens to have a prime factor p such that the group order is comprised of prime powers all less than k, then our method is going to succeed. For in this case, we are guaranteed that that prime is going to be a divisor of w. That is, Lk times P0 is going to be the zero element of the group of the points on our elliptic curve. So, how big should k be when computing this multiple Lk times P0? And how many different values of a should we try? Well, this is all kind of playing around with heuristics and making these decisions. And certain arguments indicate that if you're trying to detect a prime divisor p of m, this is going to be the size that a and k should run up to. So e raised to the square root of log p log p over 2. For example, if m happens to be a product of two 20-digit prime numbers, so that's a hard number to factor if it's only got two big prime factors, then in order to detect these primes, I would want to let k be on the order of 10,000. And if we were trying to detect 100-digit primes, I would need k to be on the order of 10 to the 10th. And that's way out of reach of our computational power. 10,000 is okay. So the elliptic curve method is quite effective at identifying prime factors with between 20 and 30 digits. But to get 100-digit primes, it's not a good method to use. Okay, so what is the running time for the ECM algorithm? So it's expected to be on this order, e raised to the square root of log m log m. So how would that compare with polynomial time? So you've probably heard of the expression polynomial time algorithms. So polynomial time would mean it should be some polynomial, some power of the number of digits of the number. So the number of digits of m is on the order of log m. And so polynomial time is more like log m to some constant, which you can express, if you want to compare it with that, as e raised to the log of this thing here. So that would be c times log of m. That's what polynomial time looks like. So in the exponent here, we have square root of log m as opposed to this log of m. So we really want to get rid of that term in order to make it look more on a polynomial type of algorithm, polynomial time algorithm. On the other hand, this is much better than brute force, which requires square root of m trials. So square root of m, that's where you're just testing prime divisors of m up to this square root. That's e to the natural log of square root of m, which is e to the 1/2 log m. So square root of log m is much better than log m up here. So this is much better. So in practice, the elliptic curve method is the most effective for detecting prime factors in the range 10 to the 20th to 10 to the 25th. It can detect much larger factors, but you have to get lucky. Other algorithms are generally much more efficient, such as the sieve algorithms, the multiple polynomial quadratic sieve, or a general number-filled sieve. If you are trying to identify some prime factor with maybe 100 digits,